Okay, so we left off here last time talking about formation of ions and how we can predict the charge of an ion. An ion is a charged particle. So these elements can become charged because they want to obtain a stable electron configuration. And that stable electron configuration is looking like this. If I can look like these guys, I have a stable electron configuration. So sodium, in this example, has how many valence electrons? 1. It wants to obtain a stable electron configuration. How's it going to do that? It's going to lose that electron. It's going to get rid of it. Because its other option is to gain 7. It's not going to do that. Because if I lose 1, I have 11 electrons. If I lose 1, now I have 10. Now I am mimicking neon. That's where I want to get. So that's what it's going to do. Fluorine wants 1 more. So it's going to accept another electron from sodium. It's going to steal sodium's electron. Sodium's okay with that because it wants to get rid of it, right? Go ahead, take my electron. So fluorine wants that electron, so it gains 1 electron. Now they're both mimicking neon, and they have a positive 1 charge and a negative 1 charge, and they can come together as a compound and form a bond between them. Okay? So here we see that happening with oxygen. How many valence electrons does oxygen have? 6. It wants 2 more to have 8. It wants 8. So it's going to gain 2 more electrons. So oxygen will gain those two electrons. It will become O2 minus. So when you become an ion, if you gain electrons, you become negatively charged. So gaining is minus and losing is plus. Okay? So it's exactly backwards of how you would consider it to be. But electrons are negatively charged. So if I gain negative charges, I become negatively charged. Okay? So you kind of have to think of that in a backwards way with these elements as they're gaining and losing. Al, how many valence electrons does it have? 3. It's a metal. Metals lose electrons. It will lose all 3 of those electrons to get back to here. Okay? It has 13 electrons. It loses them, and it becomes like neon. It's a 3 positive charge because it lost 3 electrons. Now we can predict what type of ion Al is going to become. But I cannot predict the type of ion that Ga will become. And the reason for that is because look what's in front of Ga. All these transition metals, all these D block metals. Okay? They come before Ga, nothing comes before Al. So it's easy to predict what it's going to do. It's going to lose 3 electrons. But when I have all this right here, let me ask you this. How many valence electrons does vanadium have? 2. So when it becomes an ion, is it going to lose 2 electrons? Could. It might. But it could also lose 3. Or maybe even 4. It's unpredictable. Because, yeah, I'll lose those, but once I lose them, I still have all these. I still have all these electrons, and they can go back and they can go out to the outside. Because these are lower in energy than these ones. So if I lose those electrons, these ones might come out, and then I could lose more. Okay? It's unpredictable. I cannot predict the charges of these transition metals, of these metals right here in the middle, or these ones, Or these metals. I can't predict their charges because they can be many. You can have iron 1, iron 2, and even iron 3. So I can have all of those iron molecules. I can have an iron 1, positive 1 charge that reacts with oxygen, or I can have an iron with a 2 positive charge that reacts with oxygen, or an iron with a 3 positive charge that reacts with oxygen. I can have all those situations. So it's unpredictable. What I can count on are these first two columns. I know the charges of those metals. +1, +2. I know the charge of this one. +3. It is the only P metal that I can predict. All these other P metals, like lead or tin, I don't predict their charges. Okay? There are 3 exceptions to that right here. Okay? I know the charge of zinc, cadmium, and silver. They don't have unpredictable charges. These are their charges. 2+, 2+, and +1. Okay? They don't ever change. That's always that. But everything else can be anything. Well, not anything, but it can be other multiple charges. Okay? All right. So the octet is useful to us in predicting the charges of ions, of metals and nonmetals. Okay? The transition metals, like I said, you can have multiple charges, so you can't predict them. Iron 2+ and 3+, etc. Okay, so let's look at this. Let's answer this, and then we'll talk about isoelectric and answer these after that. Okay? So calcium. What is its charge? 2. Not 2 minus. It's going to lose electrons. That means it's 2+.
But initially it's 2 minus.
It's minusing 2, and so it has a 2 positive charge. That's right. Strontium.
Same thing.
2+ as well. Sulfur. That's right. It's going to gain 2 electrons to become 2 minus. Phosphorus, right in front of it. 3 minus. That's exactly right. Okay? That's what it's going to become. Ca2+, Sr2+, S2 minus, P3 minus. Okay? Those are the ions. Now, isoelectric, what it means to be isoelectric. Let me actually go back a page and just insert one here. Okay? So, isoelectric means that you have the same electron configuration as somebody else who is isoelectric with O2 minus. Hold on. Let's write the electron configuration of O2 minus. 1s, 2s, 2p, what? 6. 2p6 because I gained 2 electrons, right? I went from here to here. So it's not 2p4, it's 2p6. That's the electron configuration of O2 minus. I fill in 2, 2. Who else has that electron configuration? Good. Who else?
Make others
What's that?
You can make others isoelectric.
Okay.
Other elements.
Do it.
Sodium
4. Sodium what?
Fluorine or fluoride.
Okay, so give me the charge and everything. Tell me what it would be. If sodium's going to be isoelectric, what's its charge?
+1.
Na plus. Who else?
Potassium fluoride.
Mg 2+. What'd you say?
Potassium. Plus.
Okay, hold on. If potassium becomes potassium plus, it will have 18 electrons, not 10.
Oh, too far down. Got it.
That's right. So potassium plus will be isoelectric with argon, but not with neon.
Yeah.
Who else is isoelectric with neon? We have oxygen, O2 minus, Na plus, and magnesium 2 plus.
So aluminum could as well.
Yes. As a 3 positive ion, it will be isoelectric. What else? I'm looking for 2 more. I think we already said fluorine. 1 more.
Boron.
No, boron not necessarily is going to do that. Nitrogen, that's the other one I want. Okay? Carbon and boron. Carbon can go either way. But for the most part, they're not going to form ions. They're just going to make molecular compounds, and we'll talk about that later. But these are all isoelectric with one another. Okay? So if I say, who's isoelectric with O2 minus, and neon's not on the list, what should you be looking for? One of these guys, right? N3 minus is isoelectric with O2 minus. So that could be an answer to that question, right? So make sure you don't think, oh, it's just neon that it's isoelectric with. No, it's isoelectric with all of those. They all have this electron configuration, all of them. So that's what it means to be isoelectric. This thing thinks I'm writing in some other language. It has like a strange Y like this as my symbol here for this page. I don't know where I got that. Okay. All right, let's go to the next page. So, is chlorine minus isoelectric with argon?
Yes.
Yes. Is sodium plus isoelectric with neon?
Yes.
Is magnesium 2 plus isoelectric with sodium plus? Is O2 minus isoelectric with F minus? Yes. So all of those are isoelectric. Okay? Meaning it has the same number of electrons or the same electron configuration. Iso is the key to that. Iso means the same. Okay. How many protons, neutrons, and electrons are in the following? Okay, so how many protons, neutrons, electrons?
19.
Okay, 19.
19 electrons.
I don't think it's 19. 19, oh, 20 neutrons. Okay. 20.
Electrons.
How many electrons?
19.
Not 19. Look at the charge.
Oh, yeah. So 18.
18. Okay. For sulfur 2 minus, protons, neutrons, electrons.
16. 18.
And 18. Gained 2 electrons, right? Good. Protons, neutrons, electrons for magnesium 2 plus. 12, 12, 10. Because I lost 2. Good. Excellent. Okay, now we're going to finish up this chapter talking about the trends of the periodic table. Okay? And honestly, once we learn one trend, a lot of the trends fall or follow the same pattern of the periodic table. Okay? Atomic size, ion size, ionization energy, electron affinity. This one, and this one will all follow the same trend, meaning they all start in the same place, and they're going to kind of do the same. Oh, I guess these two will do exactly the same thing. This one will kind of be the same trend, but just opposite, which makes no sense to you. Okay, let's go ahead and look at that. Okay, atomic size. The size of an element increases moving down from top to bottom of a group. Atomic size increases as I move down. Neon is smaller than argon. Argon is smaller than krypton. This is bigger than xenon. Okay? So as I move down, it's increasing. That makes sense because what am I adding every time I move down the periodic table? And yes, I'm adding another energy shell. Okay? Every time. So it's getting bigger and bigger and bigger and bigger every time I move down a period of the periodic table. So that makes sense. The size of an element decreases from left to right across the periodic table. So what's bigger, lithium or fluorine?
Fluorine.
Read it.
Decreases. So it's smaller. Fluorine.
Fluorine is smaller than lithium. That's not very intuitive, right? That's not what I thought would happen. I didn't think fluorine was going to be smaller than lithium. What the heck? Lithium only weighs 6.941. Fluorine weighs 18.998403. This one's heavier. It has more electrons. Why is it smaller than lithium? Well, if we consider what's happening, let me actually draw that bigger. So let's say this is the nucleus of lithium. How many protons are in lithium? Nucleus.
3.
Okay. How many energy level rings do I have around an atom of lithium?
2.
1, 2. Okay. So I have 2 electrons in the first energy level, and I have 1 electron in the third energy level. Or in the second, I'm sorry. Now let's look at lithium. How many protons are in the nucleus? 9. How many energy levels do I have around it?
2.
Also 2. I have 2 electrons here, and I have 7 electrons here. So I have 3 protons. Those 3 protons are shielded by these 2 electrons, and then they have to reach out and grab this electron. 3 protons pulling out here is more difficult than 9 protons. 9 protons, the shielding of these 2 electrons doesn't really affect it much. It pulls out and grabs its electrons pretty easily. So what is going to happen if I can hold onto my electrons more tightly?
You're going to decrease in size.
I'm going to pull them in closer to my nucleus, and the size of my atom is going to decrease. Whereas lithium, that 1 electron is just out there, just barely hanging on. What do we know about this electron? It's going to lose it. It can hardly hold on to it. It'll lose that electron. Fluorine, does it want to lose electrons? It's pulling electrons close. In fact, it wants more electrons, saying, give me more. Okay? It's pulling its electrons in nice and tight, whereas lithium has it out here. So when we're looking at the trend of the size of atoms on the periodic table, that's what we should be considering. We should look right here, starting with fluorine. Fluorine is small. Neon smaller than fluorine. We could start kind of there or so forth, but we start with fluorine because it's the first reactive element. These ones are non-reactive, so we don't consider a lot about what's going on there. Okay, we mostly look here and we say fluorine is small. What happens as I move away from fluorine?
It's bigger.
The size gets bigger. What's the biggest element on the periodic table?
What's that? How far?
That's what it is. Yeah. Number 87 is the biggest element on the periodic table. Okay? Because look how many energy levels it has around it. On that 7th energy level, it has 1 electron. just hanging out there. And it can hardly grab it. 7 energy levels out and 1 little electron out there and it's trying to grab it. Just the slightest amount of energy and that electron comes off and this francium goes just reactive. Okay? With this, it's one of the most reactive elements on the entire periodic table. Okay? Because of that. Okay? So that's why it's doing what it's doing with atomic size. That's why it's following this trend. As you move away from fluorine, the size of your atom is increasing. Fluorine starts out small, and as you move away, it's increasing. Okay, here you can see that. Here's the size of fluorine. As I go this way, it's getting bigger. As I go this way, it's getting bigger. As I go this way, it's getting bigger. Okay? So the size is increasing there. That's the trend. All right. Sizes of ions. Well, what happens if you gain or lose electrons? What's that going to do to your atomic size? So lithium is kind of big. It has 1 valence electron. If it loses it, what's going to happen to the atomic size of lithium? It's going to get smaller. Fluorine has 7 valence electrons. It wants 8. It gains another one. If it gains an electron, what's going to happen to the size of fluorine? Is the size of fluorine going to decrease if it gains an electron?
Because it would want to hold it in all tighter.
Well, but can it? Maybe it wants to, but can it? Because think about, if I gain an electron, how many electrons does fluorine have if it gains 1? How many protons does it have?
9.
I have 9 protons, 10 electrons. Can I hold on to 10 electrons as well as I could 9? Mm-mm. It's going to get bigger. So it's going to expand because the number of protons versus the number of electrons is going to, that ratio is going to increase. It's not going to be able to hold on to them as well. So whenever I gain electrons, I get bigger. Whenever I lose electrons, I get smaller. Why? Because I have more protons than electrons. And also in the case of sodium, I lost an entire energy shell. So think about this example back here. Okay? Just by losing that energy shell on the outside there, I would decrease the size of my atom, right? I get rid of this, and now this is the size of my atom. But not only that, look now what I have. I have 3 protons holding on to 2 electrons. What's going to happen? Boom, it's going to pull them in tighter. Okay? So it's going to decrease in 2 ways. Whereas with fluorine, as I add that electron right out there, now I have 10 electrons, 9 protons, it's going to expand. That electron cloud will expand out because it can't hold on to them as tightly as it did before. Okay? So more protons than electron creates an increased nuclear charge. Extra protons pull the remaining electrons closer. Ions with multiple positive charges are even smaller than the corresponding monopositive ions. Okay? So basically the thing that you need to remember is that if it loses, look at the number of protons versus electrons, and that's how you're going to decide who's bigger. So for example, who's bigger? Nitrogen's the biggest. Why?
Because it's losing those 3, so it's going to be a cation.
Not a cation, it's an anion. But you're right about that, it's bigger, and this is why. Protons in nitrogen are what? Electrons in N3 minus are what?
4. Oh no, 10.
10. Okay? Protons in O2 minus are
6, 8.
8. Electrons? Fluorine, protons, electrons, F minus. Hopefully you can now see why nitrogen is the biggest. Because it has the least number of protons for the same number of electrons. Nitrogen has to hold on to 10 electrons with only 7 protons, whereas fluorine has 9 protons holding on to 10. So it's going to be smaller because it can hold on to them better than nitrogen. Nitrogen will be bigger. Okay? So who's smaller? Who's smaller?
Beryllium.
Okay, good. Why?
Well, just that's the way the periodic table goes.
Okay. So that's true. But let's consider this. Look at lithium, protons and electrons. Protons and electrons. How many protons are in a lithium? How many in beryllium? How many electrons are in a lithium plus? How many in a beryllium 2 plus? Who has more protons? Beryllium. Beryllium's going to pull those 2 electrons in tighter. 2 electrons to those 4 protons in the first energy level, it's going to pull them in super tight. It's just going to decrease the size of that beryllium dramatically. Okay? So that's what you're looking for, the number of protons versus electrons. All right, we already covered that. So here you can see that effect. Okay? Here's fluorine. As I gain an electron, I get bigger. Oxygen. And you can see fluorine, it becomes 133 picometers, oxygen 140. Oxygen is bigger than fluorine when it becomes an ion because this has more protons than this guy, but they have the same number of electrons. Okay? Beryllium and lithium, they were bigger, and as they lost electrons, they became small. Look how small beryllium becomes, 35 picometers, because it has those 4 protons pulling in those 2 electrons. Okay? It's going to become smaller than a helium atom, who has has 2 protons and 2 electrons. Okay? So that's with the ionic size. That's how we predict that. The other 2 trends are going to follow the same pattern as atomic size. And they do that because it's the atomic size that's basically affecting this, okay? Or it's the characteristic of why your atom is such a size that affects the ionization energy. Ionization energy is the energy required to remove an electron, okay? The magnitude of ionization energy correlates with the strength of the attractive forces between the nucleus and the outermost electrons. The atomic size does the same, right? Correlates with that. So it's going to follow the same kind of trend. The lower the ionization energy, the easier it is to form a cation. So, does lithium or fluorine form cations more easily? Which one?
Lithium.
So, lithium would have a lower ionization energy. A lower ionization energy. Because it can remove electrons more easily than can fluorine. So when we talk about ionization energy, we start with fluorine and we say fluorine has a high ionization energy. As I move away from fluorine, what do you think happens to the ionization energy? Okay, instead of increases, it decreases this time. So atomic size, it increases. But as the atomic size increases, the ionization energy, the energy required to remove an electron, decreases. Okay? So who has the lowest ionization energy? No, not hydrogen. Who's the farthest away from fluorine? It's the element that has the largest atomic size. Francium has the lowest ionization energy. The energy required to remove that electron on the 7th energy level is practically none. It has the lowest ionization energy. You don't have to have a lot of energy to take that electron off. So, to remove an electron from fluorine, fluorine doesn't want to lose electrons, right? It wants to gain electrons. So if you want to try to remove an electron from fluorine, you're going to have to use a lot of energy to do it, because it doesn't want to give away its electrons. High ionization energy. As I move away from fluorine, the ionization energy decreases. Lithium has a lower ionization energy than does fluorine. Lithium has a larger atomic size than fluorine. Why? Because of its attraction, those electron attraction to the nucleus. Okay? So for the same reason, we have both of those trends. Electron, okay, well here's just showing ionization energy. Okay? Just showing that kind of pattern. Lithium, sodium, potassium, rubidium, as you're moving down, it's decreasing. Same thing with neon, argon, krypton, okay? And so forth. That's all that's really. So that's the trend for that ionization energy. Electron affinity. Electron affinity is the energy released when a single electron is added to an isolated atom. The energy released when an electron is added to an atom. So when you gain electrons, you release energy. Okay? Or you can think of electron affinity as your attraction for electrons. I want to attract electrons. Who do you think has the highest, or one of the highest electron affinities?
Fluorine.
Fluorine. Fluorine has a very high electron affinity. What do you think happens to the electron affinity as I move away from fluorine? It decreases. So this is what you need to remember. Fluorine has a high electron affinity, ionization energy. It has a small atomic size. As I move away from fluorine, the electron affinity and ionization energies do what? Decrease. What about the atomic size? Increases. Okay? They're all following that same pattern. And it has to do with the fact of the attraction of the electrons to the nucleus. That's why they follow that pattern. Okay? Okay, and that's just showing that same trend. Okay, so that's the end of chapter 2. Okay? We're going to start into chapter 3 now. We're going to start talking about properties of ionic and covalent compounds. And we're going to get into like naming covalent and ionic compounds and structures of those, which is going to be a lot of fun. Okay? Everybody loves naming. Okay. All right, so first we want to be able to understand this, we want to be able to first define a chemical bond. And chemical bonds come in two ways. You can have ionic, and you can have covalent bonds. Okay? So these chemical bonds are the attractive forces that's overcoming the repulsion of the positively charged nuclei of two atoms participating. Okay? So we have these attractive forces that are bringing molecules together. Okay? And it involves the outside valence electrons. That's what's responsible for bonding. All the other stuff inside, not responsible, because everything inside is full. Everything inside has filled its vacancies. It's happy with how it is. It's the outside electrons that are unhappy. We only have one unpaired electron, or we have two unpaired electrons. We want to fill those vacancies, and we're going to do it by reacting with something else. Okay? And once we have done that, we've reacted with something else, we have stabilized ourselves and we're happy again. Okay? So there's a few ways that we represent these molecules. We represent them. We represent the elements according to their symbol on the periodic table. So hydrogen we represent with H, carbon we represent with a C. Okay, and we show the bonds between them. We draw lines a lot of times. We're representing these things going on in a Lewis symbol. Okay, that's how we would see it. So CH4, carbon, like this, CH4, methane. We would show the carbon bonded to the 4 hydrogens. This is representing what's happening. Okay. Now a Lewis dot symbol would be something with just dots instead of hydrogens. Each line represents 2 electrons. Okay, so we would show those electrons as dots, hydrogen, 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 hydrogen. Okay, instead. So this would be more of a Lewis dot structure. The Lewis dot symbol for just the element you can represent as well by just showing the valence electrons on that element. That's what we're showing here. These are just the valence electrons. And we can do the same. So for sulfur, I want to show the Lewis symbol for sulfur. Sulfur has 2 paired electrons, and it has 2 unpaired electrons, or 4 paired, I guess I should say. It has 2, and we call these, what we call these pairs of electrons, we call them lone pairs of electrons. Okay, and it has 2 unpaired electrons. It wants to fill those vacancies, right? Oxygen. Let's see. How do I want to do this? Okay, oxygen bonding to hydrogen. Okay, would have the 2 pairs of electrons, these ones, out here not participating, and the ones that were unpaired, it pairs with hydrogens, and it forms water. Now it forms those water through these bonds. So we can see these pairs out here, we call those lone pairs of electrons. Lone pairs of electrons are the ones that don't participate in the bonds, the non-bonding electrons. How many lone pairs are on this oxygen right here? 2 lone pairs. Okay? So that's how you would perceive that type of question. The number of lone pairs on water, 2. On a water molecule, there's 2 lone pairs. Okay? All right, so that's kind of what we saw here. Here's the elements. These are their Lewis symbols for those representative elements. We're not really representing the metals in the middle because the transition metals, they do all kinds of weird stuff. So we don't represent them in the same way. Okay, so like I said, there's 2 types of bonds. You have ionic bonds and covalent bonds. Ionic bonds are the bonds that result from opposite charges. Just like 2 magnets, if you put them by each other, they're going to attract to one another and bond. Okay? That's what these are doing. If I have a positive charge and a negative charge, they attract and they bond together. And we say that's ionic bonding. Okay? It's due to the opposite charges of the ions. Covalent bonding is attractive forces due to sharing of electrons. Sharing electrons. So, what do we know about metals? Metals want to do what? Lose electrons. Non-metals want to do what? Gain electrons. So this is a great situation for ionic bonds because I have a metal wants to lose electrons. I have a non-metal that wants to gain electrons. And so they do that, and now they can attract to one another. They can attract to one another and form an ionic bond. So ionic bonding occurs between metals and nonmetals. But what if you have two nonmetals and they both want electrons?
Sure.
Sure.
They share them. They both want electrons. What are you going to do? Let's share them. So these molecules have figured this out. So if you're a metal and a nonmetal, we just transfer our electrons and now we can bond. If you're two nonmetals and you both want electrons, you share those electrons. And you will satisfy each other's outer valence shells by doing that, by sharing those electrons. Okay, so ionic bonding. The atoms achieve the noble gas configuration. Two ions are formed, cations, anions, which are attracted to each other. So they. Okay, so like sodium and chlorine, a metal and a nonmetal. Sodium loses an electron, chlorine gains an electron, then they will come together. Okay. Now, this has to do with another trend of the periodic table, and that trend is called the ionization energy. Ionization energy. Right? Did we already talk about that? No, not ionization energy. Why can't I think of it? Electron affinity, ionization energy, and electronegativity. Has to do with the electronegativity. Fluorine has a high electronegativity. Lithium has a lower electronegativity. Okay? So because fluorine has a high electronegativity, it has an attraction for those electrons, and that attraction causes it to gain electrons. Lithium has a low electronegativity, so in the presence of fluorine, because lithium's electronegativity is lower than fluorine's, fluorine will steal the electron away from lithium. Okay? And so that's where electronegativity comes into play. All right? Ions, when they form ionic bonds, okay, they do so in these crystalline forms. They form crystals. So if you think of the salt in your cupboard, sodium chloride, it's in a crystalline form, right? A lot of minerals, that's how you find them. Minerals are ionic compounds. They're salt compounds. Rocks, they're minerals. They're these ionic compounds that come together. They form these ionic bonds, and they're in their crystalline forms. Okay? And so when we represent these ions, we represent them in their ratio. We don't say, look at how many chlorines and sodiums are in this. A whole bunch. Just one single little crystal, right? You can never represent the actual number of sodiums and chlorines in a single crystal versus another one, which would be different anyways. And so we don't really do that. You just say how many sodiums are there and how many chlorines are there. What is the ratio? What is the ratio of that? Well, here sodium and chlorine come together in a 1-to-1 ratio. So we say it's sodium chloride. 1 sodium, 1 chlorine. Okay? That's how this is arranged. For every sodium, there's a chlorine. That's how it's arranged. That's how I represent it in its ratio. Its lowest formula, we say that's the empirical formula. The lowest ratio formula is its empirical formula. Okay, covalent bonding, like I said, is the sharing of those electrons. So here's a theoretical, not true situation, but if you have hydrogen only has 1 electron and another hydrogen with 1 electron, if it was going to ionically bond, one would lose the electron, the other one would gain it. And then you would form, they would come together and form H2 in an ionic bond. But which hydrogen is going to lose and which one would gain? Neither one, because they both have the exact same affinity for electrons. Neither one's going to gain or lose because they have the same attraction. They're having a tug of war against themselves for electrons. Neither one will win. So instead of losing one and gaining one, like ionic bonds would do, they share the electrons. Okay? And that's what we call a covalent bond. Look what happens. This electron and this one come together and they are shared. those electrons are going to orbit this hydrogen. And they are going to orbit this hydrogen. So how many valence electrons does this hydrogen have now?
2.
How many does this have?
2.
2. They both have 2 valence electrons. Okay? They have satisfied their valence shell by coming together and bonding and sharing those electrons, because neither one of them was willing to give electrons away. So you can see that happening here. Here's the electrons around the nucleus of the hydrogen atom. As they come closer and closer, all of a sudden now you have those electrons orbiting both nuclei. So you have those 2 electrons, now they're orbiting the nuclei. Okay? So they are sharing their electrons. Fluorine, here's another example. It's going to do the same thing. An unpaired electron on each one. So what do? We bring them together and we share those electrons. How many valence electrons does this fluorine have now? How many does this have now? They have both satisfied their octet by sharing those electrons. Okay, water. Another great example, right? We have oxygen with 2 unpaired electrons. We have a hydrogen with an unpaired electron. We bring them together. 1 hydrogen here, 1 hydrogen here. Now they are sharing those electrons. So how many valence electrons does hydrogen have in water? 2 valence electrons. How many valence electrons does oxygen have? 8. And so everybody's happy. That's what they want. Okay? Same thing here with methane. Carbon has 8. This hydrogen has 2. This one has 2. This one has 2. And that one has 2. Everybody's satisfied and happy because they're sharing their electrons. Okay, electronegativity, like I talked about, can create a situation where you do have an unbalanced sharing of electrons. So fluorine has a higher electronegativity than hydrogen. And because of that, when they share electrons, fluorine is a little bit more greedy about the electrons because the electrons are more attracted to fluorine than hydrogen. So it kind of pulls them towards fluorine more often, and every so often they'll go around hydrogen, and then they'll come around fluorine, and then they'll go around hydrogen, but more around fluorine. Because it's being greedy with those electrons. It has a higher electronegativity. So what does that do to the covalent bond? It makes it polar. It gives it 2 poles, a positive pole and a negative pole. Now this is not ionic. This is not an ionic situation where you have a complete positive or a complete negative charge. No, it's you gain a partial positive and a partial negative charge, and you become a polar molecule. Okay, so here's HF. They're going to share those electrons, and now fluorine will be partially negative, and hydrogen will be partially positive, because the electrons are going to be more attracted. So this is negative electron rich, and this is electron deficient. Okay, because it's pulling those electrons towards the fluorine, away from hydrogen. But it doesn't give them up enough to cause this to go completely ionic. Okay, if it had a strong enough attraction, if hydrogen couldn't hold on to its electrons well enough, then it would go ionic. Fluorine would completely still it, and hydrogen would become positive, fluorine would become negative, they would ionically bond. Okay, so fluorine and lithium, their electronegativities are far enough away that fluorine will actually pull that electron off. But hydrogen has a high enough electronegativity that it will hold on to it with some difficulty. But it'll still hold on to its electrons. All right? So electronegativity, and measure the ability of an atom to attract electrons. So here we see the electronegativity of different elements. So fluorine has the highest electronegativity on this chart. As you move away, that electronegativity is decreasing. Okay? So these nonmetals have high electronegativities. 4, 3.5, 3, 2.52. Hydrogen has a 2.1 electronegativity, which is fairly high. Okay? But it's not as high as fluorine's. So fluorine holds those electrons towards itself more often. Water, hydrogen and oxygen. Do you think it's going to be polar?
Oh, yes, dipole.
Yeah, it's going to pull, oxygen is going to pull electrons away from hydrogen because look at the electronegativity of oxygen. 3.5. Look at the electronegativity of hydrogen, 2.1. Oxygen does pull those electrons towards itself. The hydrogens become electron deficient, oxygen becomes electron rich, and we create poles. We create poles, a polar molecule. Okay? And it has to do with the electronegativity. So if you're one of these nonmetals with very low electronegativities, look at the electronegativities of all these metals. They're very low compared to these nonmetals. They would easily form ionic compounds. Okay? But if you have the two nonmetals pairing, they're going to share electrons because the electronegativity is not different enough to cause them to lose entire electrons or so forth. Okay? So this is the idea right here. The greater the difference in electronegativity between the two atoms, the greater the polarity of their bonds, which would be more polar, HF or HCl. So HF would be because it's 1.9 versus 0.9 for HCl. They're both polar, but this one would be more polar. Okay, so that has to do with polarity. We're not going to do a whole lot with that. But that's just the idea behind it. We are going to identify whether something is polar or nonpolar. Okay, but not necessarily through its electronegativity. Just basically understand that if you are a metal and a nonmetal, you're going to form ionic bonds. If you are two nonmetals, you're going to form covalent bonds due to your electronegativities. If you are a nonmetal and a nonmetal, will you be polar? That's the other thing we're going to decide, but not necessarily through electronegativities. There's another factor that we're going to look at. Okay, now for nomenclature, naming compounds. And this, people tend to struggle with this, mostly with the ionic part. Naming covalent compounds, it's a breeze, okay? The problem is that once you learn this method, you try to apply it to everything. You start trying to name ionic compounds the way you would name covalent compounds. There's two naming systems. One for ionic, one for covalent. You cannot name ionic compounds the same way you name covalent compounds. So somehow you need to make sure you distinguish the difference. You can identify the difference and you can name them correctly. Because you're going to want to name everything this way because it's so easy. But it doesn't work. You'll get it wrong, right? So you need to learn how to do these ionic ones. Ionic compounds are a little more complicated to name and such. Okay. Yeah, we don't need that. So that's our formula. So ionic compounds. Metals and nonmetals. We have metals and nonmetals in ionic compounds. So how am I going to identify whether something is an ionic compound? I look at the first element. If it is a metal, it's an ionic compound. Okay? That is the biggest clue that I have that this is ionic. Because covalent compounds are only between nonmetals. Ionics, it's a metal and a nonmetal. Okay? So that's my first clue. I look at the compound. If it starts with a metal, it's an ionic compound. Okay? The metal, the first element, is the cation. Should understand that. We always write the cation first. Cation goes first. The anion goes second. Okay, so that's why the first element will be the metal if this is ionic, because the cation goes first. Cations and anions arrange themselves in regular three-dimensional repeating arrays called crystal lattices. So we write their empirical formulas, not the actual number of everything that we have. Okay? Formula of an ionic compound is the smallest whole number ratio, the empirical formula. So that's how we're going to represent it. Okay, so when we are doing this, the first thing we're going to do, is we are going to determine the charge of each ion in the compound. Okay? We'll determine the charge of the metal, and we will determine the charge of the nonmetal, which will be easy to do now that you know valence electrons and how these ions form. Okay? Metals have a charge equal to the group number. Nonmetals have a charge equal to the group number minus 8. Okay? So they're just saying valence electrons, look at your valence electrons, and that's going to help you identify your charge on your compound. Okay? So, they are going to combine to give formulas with a net zero charge. That's what they'll do. So let's look at these examples. If sodium and oxygen are going to react, what will be the formula, the resulting formula of those, of the product of that reaction? Okay, so sodium will have what charge? Does everybody agree with that? It's a minus. It's a positive what? 1. You're losing an electron.
Oh, I'm sorry. I was looking at nitrogen.
Okay, that's why. So sodium is plus 1. What is oxygen?
Minus 2.
Good. O2 minus. What is the ratio of how they will come together? How many sodiums do I need to satisfy the 2 negative charges on oxygen, on a single oxygen? I need 2 sodiums. So Na2O is the formula or the product of a reaction between sodium and oxygen. Okay? Na2O. Lithium. Li, what's its charge? Plus 1. Bromine, Br, what's its charge? Negative 1. Okay? It needs one more to get there. What is the resultant formula? Li, Br. 1 and 1. I just need one of each, right? They balance each other. They always have to balance to 0. Oh, here's a good one. Al. What's the charge? 3 plus. Oxygen? 2 minus. How many of each do I need? Does this seem trickier? Okay, I need a charge. Okay. This is, you're right, you're on the right track with 6, okay? This is what I need to realize. If I have charges that are so different like this, okay, it's hard to figure out. All I need to do is I need to multiply them each by the charges of each other. So Al, if I multiply it by 2, 3 positive charges times 2 would be what charge? 6. So if I had 2 Als, and if I multiply O2 minus by 3, what is that? 6. So the resulting formula is Al2O3, and that balances to 0. Because you have 6 positive charges, 6 negative charges, they balance to 0. They must always balance to 0. They have to. Okay? So, you do the switchy thingy. That's a very technical term. The switchy thingy, okay? So you're going to switch those charges down. That works. That works. Every time that works. But what you have to realize is that sometimes it works to where you need to reduce the formula. So let's say you have Mn4 plus and you have O2 minus. They're coming together. So I switch the charges down. Okay, I get Mn2O4. That's not the empirical formula. That's not the lowest ratio formula. So what do I do? MnO2 is the formula. So switching down works every time. It works every time. I just have to remember I might have to reduce one more step. Okay? Barium. What's the charge? Fluorine. What's the resulting formula? Okay, so that's easy. BAF2. All right. So that's how I'm going to determine the formula, the molecular, the ionic formula for these compounds. What about naming these compounds? So I can determine the formula, but how do I name them? Well, these are the procedures, or I guess the rules that we would follow. For the first element, I simply say the name of the element. Sodium. So how do I name it? Sodium. NaCl. How do I name the sodium of the NaCl? I call it sodium. How do I name the lithium of Li2S? I say lithium. You just simply say the name of the cation. Lithium, magnesium, sodium, whatever it is. The last element in the compound, and these are binary compounds, so just two things. That's what we're going to name. That's what we're going to learn to name. Is just binary compounds. We're not going to do more complicated things than that. Okay. So chlorine is the nonmetal, the anion. So how do I name the chlorine? I drop the ending of chlorine and I instead say "ide." So NaCl would be named sodium chloride. You guys are like, man, Mr. Crowder, you said this was going to be hard. That's easy. Okay? It's easy right now, but just bear with me. It'll get a little tougher. Okay? Which I know you're excited about. Sodium and oxygen. Sodium oxide. Okay, let me just point out with that one why this starts to become hard. Did I say how many sodiums were in that? No, I just said sodium oxide. Why? Why don't I need to tell you how many sodiums are there? Because guess what I can determine from the periodic table about sodium. Let's start with sodium oxide. Well, I know there's a sodium and there's an oxygen. What I don't know is how many. So what do? I determine the charges. What is the charge of a sodium? What is the charge of an oxygen? 2 minus. So what is the formula of sodium oxide? Okay. Did I have to tell you there was 2 sodiums for you to determine that from the name? That's why I don't tell you. Because if it's ionic, I simply have to determine the charge. Once I know the charge, I can figure out the ratio. So I don't tell you how many there are for that reason. So in the name, we don't say disodium or anything like that. We don't do that. Okay? That's why it becomes confusing, because you guys want to say disodium. Disodium monoxide. That's how you want to name that thing. It's not disodium monoxide. Is disodium monoxide going to be an answer choice on your test? Yes. Are you going to choose that one? No, because it's not disodium monoxide. It's sodium oxide. Okay? So you have to distinguish that in your head. This is ionic. I don't use the prefixes that tell me how many things I have. I simply state the name of the elements, and from that information, because it's ionic, I can determine the charges, and then I can determine how many of each thing I have. Okay? All right. Lithium sulfide, aluminum bromide, calcium oxide. I didn't tell you how many I had of any of those. I just simply said the name of the metal, and I dropped the ending of the nonmetal and said "ide." Okay, on the ending. Okay. Now it's going to get a little trickier again. Okay. So when you have a metal that is not a metal found in the first two columns of the periodic table, it can have multiple charges. So if I give you a compound and that compound doesn't it's ionic, so I don't tell you how many of everything I have. I just show you if I give you the formula and you want to name it, how are you going to name this one differently from this one if they both have iron and chlorine? Well, I look at what is the charge of the iron. So look at this iron, FeCl3. What is the charge of the iron? I can predict it from the formula. Chlorine has what charge? -1. If I have 3 chlorines, what does that mean the charge of the iron is? 3+. So this is how I name elements, or name compounds formed from metals of the transition metals. I state the charge of the metal in the name. So I would call this iron 3 chloride. You know how you're going to want to name that? Iron trichloride and iron dichloride. It's not right. It's iron 3 chloride. Iron 2 chloride. So, what if you had okay? What if I gave you that? Wow, that is loud. You guys can shut that door if you want. Okay? What if I gave you that and I asked you to tell me the name of it? How are you going to name? It's copper. It's a transition metal. What's the name of it? Good. So the copper has a 2 positive charge. Each chlorine has a -1 charge. So this is copper 2 chloride. Okay? What if I gave you this? What if I told you your compound was copper 1 oxide? What's the formula for that? Cu2O. How do we figure that out? There you go. You got to figure out the charges. O2 minus. What's the charge of 1 copper here? Copper plus 1. It's copper 1. What does that 1 represent? Well, what you guys want it to represent is this. See, just 1 copper. You want it to represent 1 copper in the formula. That's wrong. It doesn't represent that you have 1 copper in the formula. What does it represent? It represents the charge of the copper. Copper plus. What's the formula? How many coppers do I need to balance the 2 negative charges on the oxygen? Cu2O. That is the formula for copper 1 oxide. Okay? You have to be careful. Let's try this one. What is the name for the first iron oxide here? What's its name? Iron 2 oxide. Because this has a -2, so what does the iron have? Has a +2. What's the name of the next one? Iron 1 oxide. This 2 right here does not represent the number of irons. It represents the charge. Right? So here I have a -2 charge. That means I have a +2 charge on the irons, but there's 2 of them, so I divide that by 2 and I get a +1 on each iron. That means the name of this is iron 1 oxide. Okay, what's the last one? Iron 3 oxide. -2. -2 times 3 is -6. That means I have to have a +6 over here. There's 2 irons, so I divide that +6 by 2 and I get a +3 on the iron. Or, guess what I could have done? Switchy up. It's very technical. Switchy up. Okay? Iron 3 oxide.